All right, hey guys, welcome to week 6 of our Intro to Analysis lectures. This week we're going to talk about the last section in Cummings' book in chapter 3, which talks about Cauchy sequences. Then we're going to talk a little bit about chapter 4, that begins with sequences of partial sums, and we're going to talk a little bit about series. Okay, so in week 4, we gave a rigorous definition of what it means for a sequence to converge to a limit. And so if you recall this definition, we know that a sequence converges to a limit if for any epsilon bigger than 0, no matter how small we specify, there's a capital N in the naturals such that when you go along far enough in your sequence, that distance between the terms in your sequence and your limit is getting arbitrarily small. So that was our definition for convergence. And so the sort of theme for this lecture is that we don't need a candidate for a limit to argue that a sequence converges. So let's look at some examples here. I drew, or Desmos graphed these as functions rather than sequences, but you want to think of these guys as sequences. So the first one is the square root of n. So instead of this continuous curve, we have some discrete values here. And we know that the square root function grows, right? It grows slowly relative to other functions you've studied, but it still goes to infinity. So this thing diverges off to infinity. We can let n get as large as we want, and so the square root of n is also going to get as large as we want. On the other hand, the sequence x sub n equals 2 plus 1 over n does converge to 2. So as we let n get really, really big, this thing goes to 0, and so the whole thing goes to 2. And again, I drew this as a function, but you really do want to think of it as a sequence having these discrete values. So what is the difference? Like, if we were to just look at this picture, how could we determine that this guy diverged while this guy converged? You know, what's the big differences here? And from our limited scope of the picture, we can't say too much, but the idea here is that with your square root of n, with this sequence, we can't find a large enough n so that all terms after a sub capital N stay close together. So for instance, you know, if we're thinking about this as our a sub capital N, and we're thinking about how far the terms are, you know, like all terms after a sub capital N, we're thinking about how close these guys are to each other, and not necessarily consecutive terms, but like, for instance, if I have something right here, and if I have something right here, well, these should be reasonably close to each other, but we can see from the picture that they're sort of not really close to each other, right? That's the idea here, is that we cannot find a capital N big enough so that for any epsilon that we specify, the distance between any 2 points after a sub capital N remains in that epsilon neighborhood. On the other hand, with the 2 plus 1 over n case, just from inspecting the picture, you can see that as time goes on, or as n gets larger, this thing is going to eventually flatten off to 2. And so what that means mathematically is that there is some capital N, so that everything after capital N is going to be in the epsilon. All the terms after a sub capital N are going to be close to each other, not just the consecutive terms. We do notice, though, that consecutive terms in the sequence of square root of n do stay close to each other. So, like, for instance, a sub 13 is equal to the square root of 13, and a sub 14, this is a consecutive term, the next one after a sub 13 is going to be the square root of 14, and these two numbers are reasonably close to each other. So consecutive terms stay close, but not all terms after a sub capital N. Yeah. So going back to our convergence example, the point is that all of these terms after a sub capital N are going to be very close to each other, not just the consecutive ones. So again, I'm drawing this like in a discrete way, even though the function that I had to begin with was continuous. But anyway, this guy right here is very close to this guy, right? And this guy right here is very close to this guy, and so forth. So all pairs of terms after a sub capital N are close, not just consecutive ones like we have here. And in the textbook, I think he talks a little bit about this example, and he proves that indeed this curve, or this sequence rather, does have the property that after a certain capital N, for any epsilon, you can find that that consecutive terms are close to each other after capital N. But what we're talking about for convergence is we want all of the terms after a certain term to be close to each other. Okay, hopefully that made sense. But yeah, okay, so now we have the following definition. So this is going to allow us to get convergence without knowing what our limit is. Okay, so we say that a sequence, a sub n, is Cauchy. Okay, that's our definition, is Cauchy if for every epsilon bigger than 0, there is some capital N, so that whenever you have nm bigger than n, this means that the distance between m, little m, a sub m and a sub little n is going to be small. Okay, so notice how this is different from the consecutive case. What Cauchy is saying, it's saying, okay, you give me a capital N. All right, that is the point in the sequence in which all members of the sequence are going to be close to each other. So like this could be our a sub n, and this could be our a sub m, and Cauchy is saying these guys are close to each other because they come after a sub capital N. Okay, these guys are close to each other because they come after a sub capital N. So you want to think of this as like an a sub n and an a sub m. Okay, so all terms after the capital nth term are close to each other. Okay, so that's what Cauchy is saying. And you can see in the picture here that that's exactly what this is illustrating. So here's our capital N, and this is the a sub capital nth term. And it's saying that all terms after, when m and n is bigger than n, are close to each other. So they're in this epsilon neighborhood. This guy and this guy are in the epsilon neighborhood. That distance between those is less than epsilon. This guy, the distance between this guy and this guy is also in the epsilon neighborhood, etc. So that's the idea of what it means to be Cauchy. And it turns out that Cauchy does imply convergence and vice versa, and we're going to prove that in a little bit. But yeah, this is a way that we can characterize convergence without referring to the limit of the sequence. Okay, so I took this example from your book, from J. Cummings, chapter 3. And so we want to show that the sequence, and maybe I should have put it in parentheses, but 7 plus 1 over n is Cauchy. Okay, and so we, as with all of these sort of like convergence like epsilon proofs, we want to do some scratch work off to the side. So here's my scratch work. So what do I want? I want a sub m minus a sub n to be less than epsilon. Really, this is my goal, what I want. And so I'm going to just start plugging in things and trying to figure out what my candidate for capital N has to be. All right, so a sub little m, that means just plug in a little m into our sequence. And so this is going to be 7 plus 1 over m, and then minus a sub n, which is 7 plus 1 over n. Okay. All right, so we can simplify this to give us, so 7 minus 7 is going to cancel, and then we get 1 over m minus 1 over n. Okay, and we want this to be less than epsilon. And so the annoying thing is the absolute values, and so we can, because we're trying to figure out what capital N has to be, like just like with the convergence proofs, we're trying to isolate our little m and little n. And so to do that, we can get rid of the absolute value bars with the triangle inequality. So this is the triangle inequality. Recall that triangle inequality says that we can rewrite the above absolute value as 1 over m plus negative 1 over n. It's just the triangle inequality. Again, we want this less than epsilon. Now this guy, negative 1 over n, absolute value is the same thing as positive 1 over n. So this is equal to this. And since n and m are just indexing the sequence, they're positive. And so I can get rid of the absolute value bars is the point. Okay, so we get 1 over m plus 1 over n is less than epsilon. And so the idea here is, like, I'm trying to make this epsilon, right? And so, I'm trying to make it less than epsilon. And so I want this to be, so you want this to be 1 over m plus 1 over n to be less than epsilon over 2 plus epsilon over 2, right? Because epsilon over 2 plus epsilon over 2 is equal to epsilon. Okay, and so what do we have to choose capital N to be? Well, I mean, if we say that, okay, we want 1 over little m to be less than epsilon over 2. We want 1 over little n to be less than epsilon over 2, so that when I add that, I get this. And so, just like with the convergence proofs, if I solve for little m, I get little m is bigger than, okay, and then that's going to be 2 over epsilon, and same thing for little n. Okay, and so that's it, right? Now we know what we can choose for capital N, right? Because now we have the stuff isolated. So if we let capital N be greater than 2 over epsilon, then this will work out. Okay, so that's how we do this. It's just the same exact strategy that we employed for the convergence proofs. All right, so let's go ahead and erase all of this stuff and write the formal proof. Now that we know what capital N was. That was the point of the scratch work, to figure out what capital N had to be. Okay. And we can find such a capital N by the Archimedean property. So capital N is bigger than 2 over epsilon. All right, so let's go ahead and write this down a little bit formally. All right, so we always start with let epsilon be bigger than 0. Okay, and so by the Archimedean property, choose capital N bigger than 2 over epsilon. Well, that means that if I take the reciprocal here, I just flip the inequality sign. This means that 1 over capital N is going to be less than epsilon over 2. Okay? We have the following. We're just going to maybe box this to use it later. Before we say we have the following, we're going to include our hypothesis here, which says let little m be larger than capital N. Well, again, taking reciprocals, this means that 1 over m is going to be less than 1 over capital N. Okay? And we know that by the green box up there, that's less than epsilon over 2. Okay, so each of these is less than epsilon over 2. I'm going to box this in purple. Then we have the following. So we have a sub m minus a sub n, just plugging in our values for our sequences. Okay, simplifying. This becomes 1 over m minus 1 over n. This is going to be less than or equal to 1 over m plus negative 1 over n by the triangle inequality. And by our properties of absolute value, this is the same thing as absolute 1 over m plus absolute 1 over n. Just ditch the minus sign. Since little m and little n are positive, we can ditch the absolute value bars and just say this is 1 over little m plus 1 over little n. And by the purple, we have 1 over little n is less than epsilon over 2. And 1 over little m is less than epsilon over 2, right? So this is going to be less than epsilon over 2 plus epsilon over 2, which equals epsilon. Okay? And so that's just the definition of Cauchy, and so we know that our sequence is Cauchy. So the next little result that we're going to prove is this lemma that Cauchy sequences are bounded. And so we're going to first assume that the sequence is Cauchy, and then our conclusion will be that that each of the terms in the sequence, the absolute value of each of the terms is less than or equal to some positive, some number bigger than or equal to 0. So let's write that out, what we're trying to show. We want to show that if a sub n is Cauchy, then absolute of a sub n is going to be less than or equal to some m. Alright, so that's what we're trying to show, that Cauchy implies bounded. Okay, so first things first, suppose our sequence is Cauchy. Okay, so how are we going to get what we need out of here? Well, since it's Cauchy for every single epsilon after a certain point in the sequence, all the points after that point are close to each other, right? And so just going back to the definition of what it means to be Cauchy is that for any epsilon bigger than 0, in particular epsilon equals 1, so let's write it down. Then for epsilon equals 1, there is some n there is some capital N in our natural numbers such that when you go out far enough, when little n, little m are bigger than n, this implies that the distance between a sub little n and a sub m is less than 1. So we're using a specific epsilon here to begin our proof. Okay, and so so the idea here is that we're trying to bound all of our a sub little n's, and we want to show that infinitely many of these terms are going to be bounded in the case where epsilon equals 1. But the only thing we have to worry about after we show that infinitely many of these terms are bounded is finitely many terms are also bounded. But that's easy because if you have a finite set, you're always going to have a maximum of the set. So getting ahead of myself a little bit, but this is the idea here. Okay, so we know that this is true, right? This is just following from the definition of Cauchy. And so by the triangle inequality, we have the following. Well, actually, let's write it like this. So we want to consider n plus 1. This is certainly bigger than n, right? So it says for any nm bigger than capital N, this holds true. So in particular, capital N plus 1 is certainly bigger than capital N. So this holds true in this instance. Okay, so this means that we have a sub little n minus a sub n plus 1 is less than 1. Okay, so we're just looking at a specific little m where that little m is capital N plus 1, right? This holds true for any index bigger than n. Okay, so we can do some manipulation with the triangle inequality. So we have the following. We want to bound a sub little n. So I want to do the triangle inequality trick and write this as some stuff that I can bound. Okay? So the stuff that I can bound is right here. I know that this thing is less than 1. So I want to somehow incorporate an a sub capital N plus 1 in my work. Okay, so the triangle inequality is going to tell me that, well, first of all, a sub n can be written in a sneaky way as a sub little n, a sub capital plus 1, plus a sub capital plus 1. Okay, notice that now I see this in there. Okay, and by the triangle inequality, this is going to be less than or equal to a sub little n minus a sub cap plus 1 plus a sub cap n plus 1. And we know from up here that this guy is less than 1. So that means that this guy is going to be less than 1 plus absolute a sub capital N plus 1. Okay, so we've found a bound when little n is bigger than n, right? So let's write that. So when little n is bigger than n, we have in particular less than, but I'm putting less than or equal so you can see the definition of boundedness here. So all we have to worry about, this is what I was saying before, is like, okay, this holds for little n bigger than capital N. So all I have to worry about is finding a bound for the finite many terms, a sub 1, a sub 2, a sub 3, all the way up to a sub capital N. That's finitely many terms. I just need to worry that this might not be a bound for those terms, right? There might be something that is that's actually bigger than this in that set. So how are we going to remedy this? Well, let's see. Okay, and I'm actually going to write some of the stuff I have in my notes just so I get it down and I don't forget. So let's write it down. So note that the above inequality holds for all but finitely many terms. And the finitely many terms are, let's put it in parentheses, a sub 1, a sub 2, all the way up to a sub capital N. We know that when little n is bigger than this, this guy is bounded. But we don't know what happens when little n is less than or equal to n. So we need to argue that even in this case, we still have a bound. Okay? So how are we going to fix this? Well, remember, every finite set, right? This is a finite set with n elements. Every finite set has a maximum. Okay, so there's some largest element here. And so what we're going to do is we're going to choose our bound for all of them to be the maximum of the set a sub 1, a sub 2, all the way up to a sub capital N, and then throw in the bound that we already found. So whatever is the maximum of this set is going to be our bound here. Then a sub little n will be less than or equal to m for all little n, right? If we set this condition. Okay. All right. So for all n in n, we have a sub n is less than or equal to m, because m is the maximum of this set. And so we found a bound. And also, capital M is going to be bigger than, or, well, it's going to be strictly bigger than 0, but because we have these absolute value bars here. So no issue there. So this means that a sub n is bounded. And that's the end of our proof. So our next big theorem here is going to be the Cauchy criterion for convergence. And so basically, convergence means Cauchy, and Cauchy means convergence. A sequence converges if and only if it is Cauchy. So anytime you see the word Cauchy, you can replace it with convergent, is the idea here. Okay, so let's prove this. It's an if and only if statement, so we want to do the forward and the backward direction. And so let's do the forward direction first. So suppose your sequence a sub n converges to some limit L. Okay, and so since our sequence converges to L, by the definition of convergence from from lecture 4, there exists some capital N in the natural numbers such that n bigger than capital N is going to imply that our terms in our sequence are getting close to L. And in this case, we can say that this is less than epsilon over 2. And maybe I should have put let epsilon be bigger than 0 right here. Sorry about that. Okay. So the old epsilon over 2 trick and the triangle inequality go in hand together. If you're ever, trying to prove something about convergence, the triangle inequality and epsilon over 2 is always good ideas to have. Okay, so we know this. All right, and so we want to prove that this is Cauchy, so we're going to suppose that n and m are bigger than capital N. Well, what does this imply? This implies that a sub little n minus L is less than epsilon over 2, and a sub little m minus L is going to be less than epsilon over 2, just from what we have up here. Okay? So anything bigger than capital N, we're going to have this property. N and M are both bigger than capital N, so we have this for both of these guys. Okay? So we have the following. We're going to use... so we're trying to show that this implies that a sub n minus a sub m is going to be less than epsilon. Okay, so we have a sub n minus a sub m, triangle inequality trick, a sub n minus L plus L minus a sub m, right? This thing equals this. Okay, we're just writing it in a sneaky way so that we can use this stuff. Okay. All right, and then by the triangle inequality, this is going to be less than or equal to a sub n minus L plus L minus a sub m. Well, we can rewrite the second thing by the properties of the absolute value as what we want to write it as, a sub m minus L. Okay? And then by the purple, this is going to be less than epsilon over 2 plus epsilon over 2, and this equals epsilon. So we're done. Okay, so we've shown that if a sequence converges, it is indeed Cauchy. Okay, so let's go ahead and show the other way. So we want to now show that if it's Cauchy, it converges. Now suppose our sequence is Cauchy. Then, by our last lemma, this means that our sequence is bounded. Cauchy implies bounded. Now, by last week's lecture, further by Bolzano Strauss. Since a sub n is bounded, it has a convergent subsequence. Okay, so further by Bolzano-Weierstrass, since a sub n is bounded, it has a convergent subsequence. And let's call it a sub nj, converging to some limit L. Okay, so now we're going to start our proof. So let epsilon be bigger than 0. Since our sequence is Cauchy, just by using the definition of Cauchy, there exists some capital N1 in the naturals such that again, hypothesis of Cauchy, little m bigger than capital N1 means that the distance between these guys is going to be less than epsilon over 2. Also, since our subsequence converges to our limit L, this means, just by definition of convergence, that there's some capital N2 in N, so that when we go far enough down our subsequence, so that when J, little j, is bigger than capital N2, this implies that a sub nj minus L is going to be less than epsilon over 2. Okay, and so we have these two things. And so we want these two things to be true at once. And so what we want to do is now introduce a new letter, capital J, that's going to be the maximum of these two natural numbers, because we want both things to be true at once so that we can use the triangle inequality and get what we need. Okay, so let's write that down. So we're going to choose capital J as the maximum of these two natural numbers. Then, by a discussion we had last week, we have the following. So we kind of touched on this a little bit in the last lecture. We have n little j is going to be bigger than or equal to j for each little j. And that means, in particular, n of capital J is going to be bigger than or equal to capital J. And following this, n of capital J plus 1 is going to be strictly bigger than capital J, because n sub capital J plus 1 is bigger than or equal to capital J plus 1. And so we have n capital J plus 1 is going to be strictly bigger than J. And so that means that when J is bigger than J, little j bigger than big J, we have the following. We have a sub j minus L. Okay, so how am I going to incorporate this guy right here? This is the same thing if I do my triangle inequality trick. This is just a sub little j minus a sub n j plus 1 plus a sub n j plus 1 minus L. Okay, and so by the triangle inequality, we have a sub j minus a sub n j plus 1 plus a sub n j plus 1 minus L. Okay, and so because of this, and by our above work, right, we know that these guys have to be both less than epsilon over 2, and of course I'm out of room here, but less than epsilon over 2 plus epsilon over 2 equals epsilon. And so we are done. We have shown that this guy is going to converge to L. For J bigger than capital J, we have that the distance between a sub j and our limit L is getting arbitrarily small. Okay, so that's the big theorem here, is that we have Cauchy if and only if convergent. Okay, so that's pretty much the end of the material from chapter 3. If you guys are taking this course in, let's see, what year are we in? Fall 2025. This is going to be the cutoff for the midterm exam. So The next thing we're going to start on is sequences and series, and I'm just going to talk a little bit about this and finish this off next time. But so this is the start of chapter 4 in Jay Cummings' long form textbook on analysis. Okay, so the idea here is to take some results that you learned in Calculus 2 about sequences and series and translate these results in our new language, our new analytical language that we have. So let's start off with some basic definitions. Let's say that we have an infinite series, okay? So we're just adding a bunch of numbers up, a sub k, where k goes from 1 to infinity. And we call the numbers in the series the terms, okay? And we call the sequence of partial sums S sub n, where S sub 1 is the first term, S sub 2 are the first 2 terms added up, S sub 3 is the first 3 terms added up, and so forth. So this is the sequence of partial sums. And, you know, I think there's a homework problem on this, but we're going to use this definition here that the series converges to a limit L in the reals if the partial sums converge to L. And the series diverges if the sequence of partial sums diverges. Okay, so let's look at an example. I think this one was this one in your book? I'm not sure. Let's see. I don't know. Maybe it's in the book. I'm not sure. But, yeah, I think it's in the book. Anyway, okay, we're going to go ahead and we're going to do this in a different way. You probably learned how to deal with this in Calculus 2. We are going to talk about, the so-called P-series test. This does indeed converge. And why does it converge? Well, there's a few different ways that we can think about this. So the first way is we can think about this as the sequence of partial sums of the series converges. And so let's go ahead and just write them out. So our first term in the partial sum sequence is going to be 1 over 1, which is 1. Okay. S sub 2 is going to be 1. Let's see. Yeah. Okay. Wait, let me just make sure I'm indexing this right. Alright, hang on. Let's take a brief intermission. Making sure that I'm doing the right example from the book. Yeah, okay. Okay. Okay, now I'm looking at the book, and I think I just copied this down wrong. This is not k squared. This is supposed to be 2 to the k. Okay, so let's go ahead and fix this. So our partial sums, we're going to have 1 over 2 to the 1, which is 1/2. Okay, I'm like, why does it not look like my notes? So I had to go back and check. Okay, so S2 is going to be 1/2 plus 1/4, 3/4. Sub 3 is equal to 1/2 plus 1/4 plus 1/8 equals 7/8, and so forth. So you see that S sub 4 is going to be 15 over 16. And in general, S sub n is going to be n over n plus 1. And this probably looks familiar to you from a homework problem. This is homework problem 2, or homework 2 problem 4, rather. I asked you guys to find the supremum and the infimum of this set and to justify it. Okay, and remember you found the supremum to be 1. So the idea here is we're looking at the sequence of partial sums. We have 1/2, 3/4, 7/8, 15 over 16, etc. Right? This is our sequence of partial sums, and if this thing converges, then so does this. Okay? So the idea here is that we can use the monotone convergence theorem to see this. We have that our partial sums our sequence of partial sums is strictly increasing. Well, let's just write monotone increasing. Right? Because, and that makes sense. I mean, we're adding on something to the next bit. We're getting a little bit more than the previous bit, and so forth. So the sequence is monotone increasing. And by this homework problem that we did, we saw that the supremum was 1. And so we have that S sub n is going to be less than or equal to 1. So it's bounded above by 1. And the monotone convergence theorem said that if it's bounded monotone increasing, indeed that sequence is going to converge to the supremum, which is 1. And therefore, S sub n is going to converge to 1. And so, since the partial sums converge to 1, the series converges. Okay, so that's the idea here, is to use the fact that if the partial sums converge, the sequence of partial sums converge, then the series itself converges to that same limit. Okay, so here are some series limit laws that, you probably know already from calculus, but maybe it's a good refresher to see them again. So we have that our series, our infinite series, the first one converges to alpha and the second one converges to beta. Also assume that your C is a real number, then these 3 properties hold true. Okay, so I'm not going to prove this, but yeah, it's exactly, the proof goes exactly how you would expect it to. Okay, so the next theorem is theorem 4.3. It says that if we have an infinite series that converges, then the terms in the series converge to 0. Now, the converse isn't true. So, one famous example is the harmonic series. We know that the harmonic series, and we'll talk about this later, but just as like a preview, and maybe note that the converse doesn't hold. So meaning that when I'm saying the converse, I'm saying that, if we flip the hypothesis and the conclusion around, it's not always true. So if A sub k converges to 0, it's not necessarily true that the series converges. For instance, if we have the series 1 over k going from k equals 1 to infinity, this is the harmonic series, and this diverges. Maybe I can spell harmonic, but probably not. So this is the harmonic series diverges. And so that's just a counter example of why the converse does not hold. But we want to prove the forward direction. So let's go ahead and get started with this. So we want to assume that this series converges, and we want to show that the terms in the series actually converge to 0. Okay, so here we go. So we're going to suppose the hypothesis. So suppose that k equals 1, ak converges. And we're going to let S sub n be the sequence of partial sums. So remember, if the series converges, then the sequence of partial sums also converge. Right? That was just from our definition of what it meant for a series to converge. Okay, and so by our big theorem that said we can replace the word Cauchy with convergent and vice versa, this guy, since it's convergent, is also Cauchy. And this is by our theorem 3.10. Okay, so what does it mean to be Cauchy? Well, that means that for all epsilon bigger than 0, there's some capital N in our natural numbers such that little n m bigger than n means that everybody after the s sub capital nth term are close to epsilon. Or are close to each other. That's what I meant to say. Okay? So we have this. Now notice we have s sub 1 is equal to a1, s sub 2 is a1 plus a2, and so forth. We can generalize here what writing these partial sums in terms of the sigma, the big sigma. In general, we have s sub n is equal to a1 plus a2 all the way to an. And so we can write this as a sum. This is going to be the sum from k equals 1 to n of a sub k. Okay, so that's just what s sub n looks like in series notation. So we can replace that here in our definition. Okay. So the next thing we want to do is we want to say, okay, well, we have little n and little m bigger than capital N. We want to say something about their series, and so it's going to be useful to order these indices. And so without loss of generality, we can suppose that little n is bigger than m. And I'm not going to do the case when little n is actually equal to m, but if you're interested, you should do that as an exercise. Then n m bigger than n, just by our definition up here, we have the following. We have s sub n minus sm less than epsilon. And just writing what s sub n and s sub m means, we're going to carry that down here. This means that going from k equals 1 to n of a sub k minus m k equals 1, a k is less than epsilon. Okay, so since I suppose that little n was bigger than m, when I take away the first m terms of this series, I'm just going to be, I'm going to start with the m plus 1 term and then go up to n, right? I'm taking away the first m terms here, and we have little n is strictly bigger than m. So this means that, when we take away all of these terms, we're going to start at m plus 1. We're going to go to n ak, right? Taking that difference, and that's going to be less than epsilon. Okay. So now this holds for all n and m bigger than capital N. So in particular, this holds when m is equal to n minus 1. All right, so little n is strictly bigger than m, and so let's say that little m is equal to n minus 1. Maybe I should put this holds true. Okay, and so, just carrying down our work from here, if I replace m with n minus 1, this becomes k equals n minus 1 plus 1 to n, a sub k. And so doing the algebra here, this just gives us k equals n to n of a sub k. And so we only have one term to add in our series. We're going from n to n. And so this just becomes a sub little n is less than epsilon, which means that a sub n minus 0 is less than epsilon. And so this means that a sub n converges to 0. And we are done. So that was the proof that if your series converges and the terms in your series go to 0. But again, it doesn't go the other way around. Counterexample is the harmonic series. All right, let's see what's next on the agenda. Okay, so I just wanted to kind of review this quickly. In Calculus 2, you probably talked about this quite a bit. Geometric series is a series of this form, a times r to the k. R is our common ratio between terms, and a is the initial term, like the very first term in your series. And a and r are real numbers. So just to jog your memory from this Calc 2 stuff, we have some examples here. Okay, we have the infinite series from k equals 0 to infinity, 2 times 3 over 5 to the k. So here our initial term, if we start with k equals 0, this becomes 1, and our initial term is going to be 2 times 1. And our r, the thing that we're multiplying the previous term by to get the next, is going to be this guy, 3 over 5. And we can see that this is exactly in this form. So we can just read off of the formula. The other example your book gives is here. So we can see that we don't have an explicit formula, but we can still figure out these things. Our first term in the series is pi over 2. And our common ratio, what do we have to multiply this by to get to the next term? Well, that's just going to be what? It's going to be 3 pi over 2e as our common ratio. That's what we have to multiply by to get to the next term, and so forth and so forth. Okay, so geometric series. Okay, so proposition 4.1. I'm not going to prove this for you guys, but if you're interested, the proof is in the book. You probably have seen this at some point in Calc 2. But just reminding you of this formula, if we have a geometric series, we can compute the sum in the case where the absolute value of our common ratio is less than 1. And the sum is going to be equal to our first term divided by 1 minus our common ratio. If, on the other hand, the absolute value of our common ratio is bigger than or equal to 1, then the sum is going to diverge. Okay, so as an example here, our first term in this series, so our little a, is going to be when k equals 1. So that's going to be 1 over 2. And our common ratio is going to be 1 over 2 because, if we were to write this out and expand it, we'd have 1 over 2 plus 1 over 4 plus 1 over 8, etc. And so to get from one term to the next, you have to multiply by a half. And so that's going to be our common ratio. And so since the absolute value of our common ratio is less than 1, we can use this formula to compute the sum. So The sum is going to be a over 1 minus r. And so that is just going to be 1, which agrees with what we did in a previous slide. On the other hand, this guy is not going to have a sum. It's going to diverge. Here we have our a is 1/2, and we said that our common ratio was 3 pi over 2e. And the absolute value of this guy is going to be bigger than 1, and so the series diverges. Okay, and I think that's all I wanted to talk about in terms of series this week. We're going to pick back up on this next time and talk more about the different types of tests for convergence of series. And yeah, thanks for watching, guys, and I'll see you guys in the next lecture.